pixel coordinate into this ray, this line that has an origin, the camera origin, and the direction somewhere going into space. So how we do this, what I usually do is making a struct. Not sure you guys know about this. You can create your own data types, kind of. And using struct, you can add multiple attributes like an origin and a direction. So now instead of having a fact tree, which only has 3 values, now we have a struct ray. We can use ray as a variable with 6 values, an origin and a direction. And this is quite useful to play around with functions and stuff, because now we can make a function called UV to ray that converts the UV coordinate into a ray. So now we need to do this math stuff, what we calculated, into this so that we can calculate the origin and direction. Now the origin was already like what we saw before. Where is it? Below. What we saw before, it's part of the matrix. We can just fetch it out of here. And the direction depends on this one and the rotation matrix of the camera. First of all, UV coordinate goes from 0 to 1, but what we want is 0 to be in the center of the screen, because the center of the screen is not going to rotate and it's easier to handle. So what we do is subtract a half. This means like, okay, 0.5, 0.5 would be in the center, but subtracting a half, this point becomes 0.00. This becomes 0, a half by a half, and this becomes minus a half and a half. So it's the whole UV coordinate system is now centralized into the center of the screen. And now we need to calculate. Now first, let's return an array with 2 values, the origin and the direction. Now the origin we saw we can fetch out of the matrix. M camera is like a 4x form value, which means that we have M camera 0, X, Y, Z, A. We have those values in the camera. Now, like I said before, those values are exactly those values. There are 16 values. Those are also 16 values. And the last row here is the M camera 3. And we're only taking the X, Y, and Z. So that would be the camera origin, the ray origin. Now the direction would be depending on the UV coordinate. Let me first write it and then I will explain it. Res X, res I, camera. Info res. So let's do the direction as well. UV times res minus. Okay. So what we did here, this Z is exactly what we calculated here. Z would be the screen distance. Res X or res Y is the resolution of the output, the width or the height. Depends on if we need to use a screen width, we use here the screen width, or the screen height, depending on the view angle method, what we fetched here. And that's in camera Y. So what this does is either it returns res X when U camera Y is 0, view angle method is 0, or 1. This returns 1 and then returns res Y if it's 1. So we do half of it, like we did here as well. And we divide it by the tangent of the angle. The angle is in Euler angles, so we need to use radians to convert it back to radians, and also half of it. So this gives us the screen distance. And then the direction would be like this, though we need to normalize it, which means that the length of this vector becomes 1. And this is very useful to do the actual raymarching where we jump every time. We can just scale this direction and jump into space like that. Might be confusing, this part. This is, I guess, the hardest part of the whole workshop. So if you don't understand it right away, it's not really a problem, because yeah, it's just this part. So we have now a direction, though this direction is based on just straightforward, being the camera is looking down the z-axis. Oh yeah, the reason why I do minus is because the camera is on a positive by default. Move it back to the origin. No. Yeah. Now it's back to the origin, and the origin is at positive z. So the camera is located at 0, 0, positive z5. So it looks down the z-axis. That's why the minus is here. But it's not the camera direction. We still need to take in consideration that you can move the camera around. If we move the camera around, you see all values changing, not just the location, but also the direction, the rotation. So how to do this is a little bit of linear algebra as well. We can multiply. If we do this, mat3, we only take the 3 extreme matrix of the matrix, which means the first 3, second 3 here, and those 3 together form a matrix, and that's the rotation. And we can multiply that with the direction. And then we get the direction oriented by the camera. Now, to test this, it's always good to test this if this works, is now first calculate array. Is UV to ray, UV. So now we have this ray object. And with this ray object, because it has 2 attributes, we can do ray dot direction. And this gives us the factory direction. And now we're going to output it as a color to see, like, okay, how does this look? And it looks like colors. If we go back to the origin, that's the easiest to check. So what we see now are the values. This is the value of the direction. So what we knew is, like, right now we are standing at the origin 500, and we know, like, okay, the middle pixel would be straightforward. So this should be 0 because we're in the center, and this should be -1 because we're going straight forward, straight down the z-axis. And we can check this with we can check this if we view the top with this plus thing. We can press D to get, like, information of the pixels, and this is very handy to see, like, okay, what's going on. And then if we go closely to the center, you see the R and G being, okay, now everything is clamped to 0 here. And that's because the output is set to use input, which is 8-bit fixed. And it means it's between 0 and 1, and we cannot have negative numbers. So let's change this to 16-bit. Okay. If we now go through it, yeah. So in the center, as you can see, can we press it? No. As you can see, the red value is 0, G is also 0, almost, and B, the Z-axis is almost -1. And if you go to the left, Z becomes less, X and Y is because of the UV coordinates. And to see like, now we're looking forward, but if we drag it to look upwards, everything becomes green because we're looking up. To the right, everything becomes red, and to the back, everything becomes blue. So in this way, you can debug a little bit like, okay, what's going on? Are all values okay? And this seems to be all right. So then we can continue. Yeah. So now we have an array. We can also check the origin, but the origin is the same for all pixels. So all the pixels has the same color, 005. And if you move it away, struggling a little bit with the windows. If you move it away, you see the color changing as well. All right, let me look back at the. Yeah. So now we have a camera, and now we can do the magic stuff, and that's the raymarching itself. Yeah, let's minimize this one. Let's delete the code. Okay. Let's make a function. If we also take the other one, take this one with us. So, okay, we now have this angle, this array. We know the origin and the direction. Now it's time to do the raymarching, to do this process of like asking what is the distance to any object in space, jump that amount and do it again. So it's a for loop, it's a loop that we ask every time, every iteration, we ask the distance and we jump further until either the distance is super small or super big. So let's make a function that returns a distance to returns the final distance to the object. So after a few times raymarching like that, a few steps, we eventually end up either with an infinite long ray or a certain distance. So we need to make this march function that returns this final distance, either -1 or 1,000 or something, or this exact distance. So let's do that. It's a float distance, march, and what we know is the ray, in what way we want to render it, and maybe a max distance that we're not going to continue forever because it doesn't make sense. The amount of steps that we have to take, I mean, the first step, of course, we don't hit all the rays yet. So it takes a while before you get closer and closer to the objects. As you can see, like the white lines didn't reach anything yet. So they continue. So about, in this case, about 23 steps we need to take before we can render everything, or even more, 28. And that depends really on the geometry of your scene. So we'll see that in a bit, what happens if you have too less steps or too many. Makes things, you can never have too many, but it makes things slow because yeah, you loop that many times. So we have a for loop to the max march depth. what I'm usually doing is make a define for this. This is something that before runtime, when the shader gets compiled, this value is filled in here. It's just an easier way to change this quite rapidly because the code is becoming quite long. And then you can just scroll to the top, change this to more steps if you like. Let's start with 32. Okay, and in this loop, we need to do a step. We first, let's go back to 1. First, we need to ask some kind of distance. Okay, give us the distance to objects from any kind of position. Like this march function is finally returning the distance to the final object. But now we want to have a function, let's call it C, that gives us the distance to any object from any position in space. So position, factory position. So what is this position? That would be stepping over the ray, ending up at some location of the ray, and it changes for every step. First, we start at M camera, the camera origin, and then we jump and we end up somewhere. And how do we jump? Well, that we can use the ray for. We start at the origin, and then we add direction times a certain depth. Now, this is why we normalized it here. This direction is now length 1. So the amount of depth is just a float. Let's start at 0. It jumps that amount into the scene and gets like, okay, we start here, M camera. Let's say the depth is 1. It jumps 1 into the scene, into the direction we calculate before. So we kind of get this. If depth is 1, everything jumps at the same thing. But depth isn't 1. Depth should be the distance to the scene, which did we do here, distance to the objects from that position. No, that would be just only the distance to the object from the position where you are. So we need to add it. So eventually depth would be the current depth plus the distance to the objects. That would be the next step. But unless this distance to the object is smaller than a very small thing, that's when this is happening. The distance to the object is so small that it cannot really jump further anymore. So if this is happening, we hit some surface, hit object. And then we can just return the current depth plus the distance object because we didn't add it yet. We're adding it just here. So this will be the depth that has been walking through the line. So we really know the distance from the camera to this surface point. What we still can do, if the depth exceeds the max distance, then break as well. Or return, let's return 1,100, like far away. Or, yeah, no, let's do it like this. So jumping over the ray, checking the distance, we need to write this function. If the distance is smaller than a certain value, an object has hit, and we return the depth, which started at 0, but it's being increased by the distance, by the steps. If the depth exceeds the max distance, we didn't hit anything, and we return a big number. If it's eventually, we didn't either hit the max distance or the distance object, which means kind of we have 2 less steps, we also just return, for now, we just return the background. There are some tricks we can do in this function to make it look better, but yeah, that's more in detail. It's not very necessary for now, for the concept. All right. So let's run the function. What's ray? Now let's do a max distance of 10. And this gives us a distance to object. Now, to know the position of that distance, because we just return only a float, the distance to the object, we can do the same thing again, cast array. It's called casting. Ray origin plus the direction plus this distance we just calculated. There's some position in space that we end up in. So let's now build this scene function. This is the actually environment, the scene we're going to render. So this should describe the distance fields, what we talked about this yet, of all the objects, and return the distance to the closest one. Now, what we saw in the beginning was with length, we could draw circles. And this also works in higher dimensional space. In this case, we have 3D. So length also works in 3D. And we can subtract some kind of radius. Now, this gives us, return, this gives us the assigned distance function of a sphere. If it's outside the sphere, this B, if it's somewhere here, the distance is bigger than the radius, so this becomes positive. The radius is 0.5. But if it was inside, it becomes negative. So this gives always the distance from any point in space to a sphere. And yeah. So let's see what this does. Again, we're looping until we hit something, a sphere. If we hit it, we return the distance. If not, we return a big number. Now, what we can do, if the distance object to object is smaller than 100, which means we hit an object, then we can color the position just to debug again to see if everything is okay. Let's include alpha as well. So jumping in, finding the distance, then finding literally the position and outputting the position. And there we go. We have a sphere. Now, as you can see, it colors a bit. Yeah, it's the same way what we saw just yet with the direction, because now, okay, this top of the sphere is a positive y, so that's why it's green. Why is this red? Because I wasn't centralized. Okay, now we're in front of it. So this is green, left is or right is red, and in front, because we are looking from z positive down to 0, so everything in front is blue. It's more closer to us, so positive z. So yeah, this is a nice sphere. And let me see. Yeah. What we need to do now, we have now position in space. So looking at this again, we know now where we are, but that's not the only thing we need to know. What we also need to know is the normals, and the normal, a little help, a tool for that. Imagine this is a surface of some kind of object. And we found the position where we are, the cross, the center of the cross. We found by raymarching, by finding the position there. But now what we want is the normal, and the normal is a vector that is perpendicular to the surface, so it's pointing outwards. Made it this one. So it's the blue line here. This blue line is what we need to find. And how we can do this, and this is a little bit confusing maybe as well at first, but play around with it after if you like to understand it more fully. But what we can do is getting the endpoints of those cross, but then like the cross being very small, and finding the distance to the surface at the red circles here, and also on the Y, also the green circles. And if you subtract them, you kind of rotate the whole cross in the direction of the normal. So it's a little trick to find this blue line. We can just sample, find the distance from a little bit above the surface, a little bit underneath the surface, and a little bit to the left and right. How this looks like in code is we need a function that calculates the normal from a certain position we are at that moment. We are here. So what we can do is sample, which means getting the distance from P plus some small displacement to the right. Now doing this is a bit nasty if you want to change this. So what I usually do is making a fact2 with a 0 and a small displacement. And then we can just do like this. So it fills in 0.00100. And if we subtract the same from the other side, and we do this as well for the Y, and also for the Z, we end up with a fact3 like this. And it's a little bit magical, but this ends up to be the normal, that being the line perpendicular to the surface. Only thing is that we need to normalize it. It should also be the length of 1. And I'm going to return it. All right, so let's look at this. We found the position, so now we can calculate the normal. And it looks like this. Quite similar to the position. That's because the position of a sphere is kind of the normal. It's pointing in the same direction. But it's more bright because it's normalized. It's length 1. But this looks quite good. We need this vector for the light. We'll see in a bit. But for now that we have it is good enough. And the thing is here to why this works for light. If you only plot, for example, the Y direction of the normal, you get already a nice kind of shading. Feels like the light is on top of it because the angle smoothly is less and less. You get like a nice shading kind of feeling. Little moon. All right. Yeah, so objects. What we just did was making just a sphere, but we want to have more objects. Let's do this back to the normal. So if we want to have 2 spheres, for example, the distance to sphere 1 would be this. This to sphere 2 would be this, but moving it away from it. Sphere position 2. So now I have 2 positions, 2 spheres, and I'm returning the minimum of the 2. If sphere 1 is closer, it returns the distance to sphere 1. If sphere 2 is closer, it returns the distance to sphere 2. Let's move it a bit away. Now, here I have it. 2 nice blobs. Now you can change the radius and stuff. So the position, this feels a little bit weird as well, like the distance function that we talked about before. It felt like upside down, like the other way around. It's the same like this, like to put a position somewhere, because we are evaluating from a position, it's the other way around. You're not adding the position to P, but you're subtracting it. So like what we did to centralize the image, we subtracted a half to make the half the center. And that is a bit confusing, that it feels like the other way around. You get used to it, and that makes sense. Okay, but this is just a sphere. A sphere is the most easiest shape we can make. And there are multiple different kind of techniques. I won't go into it mostly in depth, but let me write one for now, a box with a position and a scale. Scale. There's this guy, Inigo Quiles. I'm not sure you pronounce his name like that, but IQ. And this is the most genius shader coder there is. And he really made beautiful articles and videos about like sign distance functions, especially the box as well. Also included in the references. So if you're curious, you can check that one out. But it would be something like ops position minus half the scale, and then return the length of max. So I'm not going to explain this fully, because also it's it takes like an hour or so, because you need to draw it, and now it's very hard to understand like what is happening. But this is because if you do all the math, you eventually end up like this. Also, a reason why it's, in my opinion, not a very good idea to learn shaders by reading other people's code, because the code looks like this and you have no idea how they came there. In my opinion, it's better to try yourself, like starting from scratch, try to write stuff and try to understand the math behind it, get like huge code, and then make it smaller and smaller and smaller. So you eventually understand it better. So box position and a sphere position. Make a box now as the box P. Box position. And then, I don't know, 2, 3, 1. And return either the sphere or the box. Okay, a little bit bigger. There we go. As you can see, the normals again, it works as a charm, because we just doing it numerically. So we can, it doesn't matter what kind of shape it is, it will always find the normal, because we're doing this. It is, however, quite heavy, because we have to do the render the scene kind of like 6 times. There is a technique to do it in only 4 times, but I didn't include it here because it makes it even more weird. Because then you use a simplex instead of like now we're doing X, Y, and Z, and then you can do it in only 4 times. Also, again, IQ has wonderful articles about it. So if you really want to know it, then check that one out. Yeah. Now, what is not so nice is this hard cut. It's nice that we have like multiple objects and we can combine them, we can move them around. For example, if we make a uniform box position, this way we can include some kind of position in our uniform. So now we can move it around. Yeah. So this doesn't look so nice. What we would like to is smooth this out a little bit. And there is some trick, again, IQ, wonderful article about it. But I made it to get a little bit of a feeling of what is happening. It's like, okay, now we're taking the minimum distance of either two. To show this, I made this little guy. Imagine this yellow line is the distance to an object, x, like in the width, this is the position in space, and this returns some kind of distance to an object. So at this position, the object is the closest. And then you have other kind of square kind of thing. There's also a distance function. So this is the distance from that object. Here, in case it's the closest to this object. And if you combine them, what we did with min, you get this shape. And here's this hard cut we're talking about, like what we saw here. This hard cut is this thing. Now, what we kind of want is to smooth this out a bit. And I'm not going into it again in depth, sorry about that. But I made like the steps, what we're doing here. So going through it quickly. We need to find like the intersection. Where does this intersect? And we can do this by subtracting one distance to the other and take the absolute value. And you get something like this. It becomes 0 where they intersect. It becomes bigger than 0 where they don't intersect. Now if we flip this around, so this becomes negative and we add a little bit, we get more like this shape, and then we max out the negative. So we really get like a signal where the two meet. We have like a nice spiking feeling. If we now smooth this out by some math to do a quadratic out of it, then this becomes like smoothie, and we scale it down a little bit, and this we subtract from that. Then we get this nice smooth behavior. It might feel like, okay, what's happening here? It's magic. But again, yeah, in the reference, I wrote down like where to check out in detail how this min function works, and also some other techniques you can use as well to smooth this out. But how this looks like in code is, so this is the problem, min square box. We need to have some kind of smooth version of this. So let's make a function smin, smooth minimum, two distances, float A and float B, and some kind of value how smooth we want it. And now what I did here, I'm not going through the math in detail, but it looked like this max the absolute value of A and B, we negate it, we add a little bit, we max 0 it, and we normalize it. And A, B, and minus, subtract this quadratic form. That. Let's see if this works. So this is exactly what I showed you at this tool here. But yeah, it might be confusing. So if you really want to know the math behind it, I advise you to check out the video of IQ. But for now, it works. Now we can, if we move this box, you see it blends nicely. Okay, we have some artifacts here, as you can see, like it's a black line. That's mainly because we have 2 less steps. Like I said before, like we were stepping in the world, and some of the rays, because they are very close to the surface, they don't end up reaching the end of the surface. So if we increase this to 64 or something, then those lines will disappear and it really gets more smoothly. Yeah, this is a really nice technique to make more organic forms. What we're also going to do is, like, if we look at the start image, we're using it here as well, because eventually this what you're seeing here, this is just a tube. This is a tube deformed a little bit, and this is another tube, but like white, and then smooth, meaning the smooth blending the two together. And you get something like this. And then, of course, the deformation, but we'll see that in a bit as well. Oh, we're going to see this now, the deformation. Yeah, the thing is, what we saw with the distance function. Lost it again. Yeah, this one. Oh, this one is better. Like this rectangle. Like the function we're creating, it's giving a distance to the surface, like what we saw. Or what we now can do is maybe adding and subtracting a little bit of difference per where you are, like maybe the angle from where you are to the center, or just the position in space. So deforming space a little bit, and this will result in like deforming the surface as well. I mean, if this suddenly this position would be here, then also the surface would suddenly go up and down. So to see what is happening, we, for example, can have this radius, the radius of the sphere. Let's call this R. We can, for example, add something to it. Let's say, let's do noise straight away. There's a nice function in TouchDesigner TD simplex noise. And it returns, it's quite heavy. So you shouldn't do this all the time, but for now it's okay. It returns some kind of noise, quite similar to the noise stop, simplex noise, though without the harmonics. So something like this. Return something like this, depending on the position you're giving it. So let's do P. So we're getting a noise field of the position where we are at that moment, and this value returns value between -1 and 1. So let's scale it down to 0.1. And let's remove the box for now. Okay, now you see already it's a little bit deformed, but the frequency is not so much. So if we multiply the position with 10, for example, okay, this is way too crazy, by 3. Now you can already see a nice like weird shape, but if you move it around, you see it's like jittering. The distance is not correct, and at the same time it's weird. Sometimes it looks good, but moving it around, you get like weird stuff, and that's because it's not a real distance. This was correct, this length, and then minus the radius, though the radius is changing based on where you are. So it could be that at one position it's 0, but at the other position right next to it it's 1, and then suddenly the distance is way less. And what happens then, I can show you with this guy. What happens then? Yeah, here for example, here I made here I did exactly that. It's a circle, but I displayed the distance by a sine wave. So depending on the angle, it gets a little bit more or a little bit less. So you still get like lines, and some lines they do end up at the surface, but as you can see, some lines don't. They end up inside the surface, and that's a problem, because then suddenly, yeah, you're inside the surface, and we want to end up being at the surface and not inside the object. So that is a little bit nasty. That yeah, there are some fixes though, some hacky fixes. For example, multiply the distance we want to jump by a number smaller than 1. So we are not jumping the exact distance of the white line, but like, for example, 0.6. And then we end up here and do the same thing again. So then the chances are way less to end up in the surface, but it will cost more steps to end up at the surface. So it's a last resort kind of thing. The best way would be just to keep it as close as possible to a distance field, a real distance field, and eventually do tricks like noise and stuff in the end, and then yeah, do some hacky trick to make it work. So for example, this gives us the float sphere. If we now, instead of returning this sphere, but 0.9, still a bit crazy. Do a little bit less even. One more time. Yeah. So now we have now it looks better, but it takes more steps. So eventually it's too expensive to do it. That it cannot be done real time if you do it all the time. And as you can see here again, we have a problem not reaching the surface, and we get a black line. So increasing it even more will let you get there, but again, yeah, it gets more and more expensive. If you don't have a good GPU, that can be a really big problem. Let's include the box again. Oh yeah, also a nice thing is that you don't have to multiply it with less than 1 for all the distances, but only the distance that you are that is not a correct distance. So we multiply it only with the sphere, and then we can still use a box and blend it. And then you get like crazy behaviors already. This is also a really nice, powerful thing about raymarching, to build objects like this in normal rasterizing, like with normal vertices and faces and stuff. It can be quite tricky, and you need a lot of vertices and stuff. And because we are just talking about distance functions, we can do crazy stuff with this. Still some side effects. Well, now, what we want is not like some weird bloppy in a box, but we want to have some liquid water falling down. So we need, like I said before, we need tubes. And a tube is also not a very hard distance field, because it's kind of the same like a sphere, but instead of doing a length over x, y, and z, you only do a length over x and z, for example. If you do this, I'll show you. You turn length pxc minus 0.1. Now we get an infinite tube, because it just only checks the distance on the x and the y and not over the y, x and z and not over the y. So eventually, for any y, you get the same distance. Now you can max this, but dangerous again, this doesn't give you a real distance. To do a more fancy trick like we did with the box. But for now, show you that you can, it now returns the length to the infinite tube, unless py is positive, because if it's positive, then that one becomes is bigger than the length, and then it returns that one. So everything being positive y returns y. So you get like just a surface. Now we can take the absolute value of y. So the negative is the same thing, but we need to subtract a little bit, and that would be the height of the tube. Now to do this proper, get a real distance, it's similar to a box. We do then, I think it was something like this. Length px. Yeah. Yep. Error. P. Yeah. So it's exactly the same what I'm doing here. The only thing is this makes it a real distance function, like the box as well, because else you get side effects. If you look at a certain direction, again you go into the object, and then it doesn't look good. For all those distance functions and stuff, there's again in the reference, I will show you later, there's a list of a lot of those, and they can become quite complicated and not so obvious. So yeah, you need quite some math to design them yourself. For me, it's a little bit beyond. But IQ is, man, this guy, he knows everything. So definitely describes every object very, very clearly to understand what is happening. So we have a tube. Let's call this water stream. And it's a bit bigger. No, it's a bit taller. This feels weird. Should be the other way around. The width should be, oh, the height should be Y, and the width should be X. So height Y. Let's return the water stream. Oh, it was correct. Length. Yeah, it was correct. Yeah, like that. Okay. Let's add one more. Water, let's call it surface. And that's a bigger one. And not so high. And we move it to the bottom. Take a minute. Water stream and water service. Maybe a little bit more. A little bit less crazy. Something like this. All right. Yeah. Next, we're going to do the lighting, but I think it's better to have a little break right now and then come back in 10 minutes.